Good evening, everyone. Everyone. Welcome to the big third of problem-solving session on industrial wastewater treatment. Uh, the course instructor for this subject is Professor Alok Sinha and Professor S.K. Gupta from IIT and ISM Dhanbad. My name is Manyatnam Prakash and I am from IIT Kanpur. As usual, this session happen on every Tuesday from 6 p.m. to 8 p.m. and the link for which has been already shared with you. And the recording of this. Good evening, Sneha ji. Hmm. And the recording of this session will be uploaded on the YouTube channel, and the link for which has been already shared with you. So if you have any kind of doubt, you can just go and check those videos. Okay. So in week 3, these two topics were discussed, that is gas transfer and air stripping. So like how one contaminant is getting trapped in water and all these things and how it can be removed. Several methods, several process was discussed, and there is something called advanced oxidation process. Okay. So so this session will be conducted in a two way. There will be maybe 5 or 10 minute recap of what has been discussed, and I have certain set of question that I will be presenting it one by one, and I would request you to like participate in and see whether you are able to give correct answer or not. Those question will be asked in your final assessment or the assignment which you are getting currently for weekly assignment. Okay, so the most of the question will be similar to what you are getting currently for your weekly assignment. Okay, now, so if you have any kind of doubt, you can always write in chat box. Chat box is always open for everyone. This chat box is open, and or you can unmute yourself and you can speak directly. There is no any kind of restriction or all these things. Okay, just if you have any kind of doubt, you can ask anytime. Okay. Where does it go? So this is a small recap of it. Will hardly take 5 to 10 minutes. Okay, now so stay here, just listen to what I am saying, and then we will be proceeding toward the question and answer, that is problem solving session. Okay, now. So, gas transfer and air stripping involve the removal of volatile compounds such as ammonia, volatile organic matter from water by transferring them to gaseous phase. So, we know that there are several sources of ammonia and volatile organic compound in our industrial waste, and we have to, if we want to treat those wastewater, we have to remove these things. So, there are certain process which governs that how these dissolved gases or which is mixed in the water, the gases which are mixed in water can be removed. There are several processes that you have already. I am assuming that you have already watched your video. That's why you will be able to recap these things in a very easily manner. If you are not gone through the video, no problem. Just be here. You will get some idea what we are discussing and what type of problem we will be solving. Okay. This is achieved by bringing the contaminated water in contact with the air, often using stripping towers. So, all of you are must aware of what is this stripping towers, and we transfer our contaminated water here. There is exchange with oxygen and other gases, and there are some process involved which helps to treat our industrial wastewater. The key principle is Henry law. Okay, so there is some this famous Henry law that say that concentration is proportional to the partial pressure of. I I hope you must be aware of this thing. Okay, so by that principle, either a gas is either dissolved or redissolved from one water. So with the help of that principle, we can maintain certain kind of pressure, or we can maintain certain kind of concentration, and that will help to remove our dissolved gases. Okay, now air, then there is something called, see, these are key aspects when we are talking about the key transfer. Then the principle is simply this Henry law. We use this Henry law concept: partial concentration is directly proportional to partial pressure and this thing. Then there are certain numerical value, numerical formula, Henry constant is used. Then there is something called air stripping tower. Typically consists of packed of media to increase the contact surface area. We know that if we increase the surface area of our system, then there will be more expo- there will be more transfer of gases from our liquid sample to outside the atmosphere. So for that we use air stripping tower. Okay. Then the we in then there are some other things which affect the efficiency. First, we have already discussed the Henry law constant of the compounds. Okay, now we will be seeing that what is this Henry law constant. And I think you must be aware there are some constant. Depending upon that constant, either your gas will be redissolved in your water, it will be dissolved in your water, or it will be removed from water. Okay. pH is ammonia. Then there is a pH concept that depending upon the pH condition, either a gas will be dissolved or redissolved. Okay, now temperature, higher temperature, more randomness in the gas, it will pass, it won't stay in the water. Pressure, as we know that partial pressure is directly proportional to dissolve this concentration of any gas in water. Then if we increase the pressure, then there are high chances that gas will dissolve in the water. If we remove that pressure or decrease the pressure, then there are chances that it might not dissolve. Type of the packing material in the tower, that is structure versus dumped packing. Means this is for to increase the surface area. There is a structure, a stripping tower. If we, how we are packing our structure, like are we providing enough surface area or not, or we are just dumping it so that there is a decrease in surface area and all these things. Design approach, these things are equilibrium, estimates the stripping performance based on the mass balance. It's like simple, like if we are designing something to remove our way, then we have to make sure that all the fundamentals law are being followed, and we will be depending upon those law, and we will be finding the efficiency or design parameters of our towers. Dynamic approach is there, that more detail and consider real time stripping behavior. These are something related to your design purpose. Then we have application. There are several question, several example has been shared, and the most discussion was focused on ammonia. Okay, now then the other gases. Then other important thing is that VOC, volatile organic carbon, can be also removed from the wastewater treatment, especially for the site contaminated by industrial. So this gas transfer and stripping is used in groundwater treatment for site which is affected by industrial spills. Okay, now because we know that suppose there is one gas which is producing, there is a factory which is producing some kind of ammonia, and obviously that ammonia, if ammonia will be released, then it might, there are high chances that it might get dissolved in water, then that water is not suitable. Then we have to treat it. Then we have to go through to the function, this concept of gas transfer and air stripping. So this was all about this gas transfer and air stripping. Okay. The second thing is this advanced oxidation process, AOPs. Okay, now not till we were looking into, like if something is dissolved in or something is get has been dissolved in water, then how we can be mainly gases. If some kind of gases or anything has been, suppose has been dissolved, and it can make get transferred into water, into gas, then those concept were used, that concept of Henry law. Then we have to build air strip and all these things, airstrip tower and all these things. Now another process of treatment is this thing called advanced oxidation process. Just let it wait. It cannot be more small. Hmm. AOPs are treatment process designed to degrade complex organic in water by generating high reactive species, primarily radicals. So what will happen that in very simple oxidation so first let's understand what is the simple oxidation, not advanced. Simple oxidation is there if there is some organic matter, say C, there is some organic matter, suppose say CX, uh, A- H by and O something O X by Z. Suppose we have the simple organic matters. Organic matter are in the form of CHO. So what will happen that if it's come contact in oxygen, that is O2, then what will happen that this oxygen, due to this oxygen is very oxidizing in nature. So what will happen that it will oxidize this organic matter, and then we know that we will be getting CO2 and all this thing. Okay, na CO2, then H2 and all this thing will be produced. So these are simple thing, like in presence of oxygen there will be some oxidation, and it will get this organic matter will get converted into simpler form, that is CO2 and all this thing. Now in advance, like here, instead of O2 we will be using some more oxidizing material such as hydroxide radicals, that is OH dot. This is way to write hydroxyl radicals OH then dot. Okay, now it is very it is very reactive. It is very high. It has very high what do we call oxidation power, and this will be used to oxidize any organic matter, maybe more complex organic matter. See, simple one can be easily oxidized with the help of O2, but for complex matter, we need powerful material, and there we use these radicals. Hydroxyl radical oxidize pollutant, breaking them into simpler and often non-toxic molecules. See, you have already seen some of the examples. If not, then I will request you to go and see those examples. Then you can easily understand. Some of the common are ozone, waste OAP such as ozone slash, sometime ozone and H2O2 is also used. Sometime ozone plus UV is also used. Then we have already seen UV waste, which are very generally used. Then there is something called Phaeton's process, where we used iron in presence of F2O2. This has been discussed in your lecture. What is this Phaeton's process? Then we have sulfate radical waste OAP. Okay, then that is for sulfate. Sulfate, that is SO4 2 minus. There we use the radicals. Similarly, there as hydroxide, there is radicals of hydrox OH minus. Similarly, there is radicals of sulfate, and we use that radical for oxidation process. Then we have electron photon process, ultrasound assisted OAP, photo. These are some of the examples. Okay, now fluorine is also used. Now, if we look into the oxidizing potential, then fluorine is very oxidizing in nature. Then we have a hydroxyl radical. Then we have ozone. Then we have hydrogen peroxide, that is H2O2. Okay, treatment of recal or the miss I don't recall what is the meaning of this term, so sorry for that. But you can say that if we want to treat some complex organic matter present in industrial wastewater, then generally these type of radicals are used. Enhancement of biodiversity in wastewater before biological treatment. See, if you look into the treatment plant, then we know that we have primary tank, then something secondary tank. Then we know that we cannot directly dump our our industrial wastewater directly into sedimentary tank. We have to break, because we know that in industrial wastewater there are high chances that the organic matter which is there will be in the form of very complex nature. Then we have to break down those organic matter. Then there we will be using these radicals, that is OH mine, OH dot, sulfate waste, H2O2 waste. Disinfectant through, though limited due to short time of like disinfection is also used. You might have heard UV is used for disinfecting. Means disinfect means we are saying that we will be using to kill bacteria or any pathogens. We know that UV are used, then H2O2 is also used to kill pathogens and all these things. Okay, so these were some of details about this gas transfer and this oxidation, advanced oxidation problem. Anyone have any doubt? If no doubt is there, then from next onwards I request everyone to please participate, that there will be some question one by one, and I request you everyone to write in chat box what will be the correct answer, and then based on those answer we will have discussion. Okay, then first question is this thing: non-strippable compounds are those whose Henry law constant in atmospheric in atmosphere constant in this is the unit moles of water divided by moles of air. Okay na. So, and then if non-strippable compounds are there, if, from the name you can see non-strippable and strippable. Strippable means those compounds which can be easily removed from water. Then what will be their Henry constant? And non-strippable means those which cannot be removed from water by easy means. Then what will be its Henry? We have got one answer, that is A, less than 0.1. Okay, good. Okay, then I will be moving forward with the answer. Then this is some basic example of a strippable versus non-strippable compound. When a compound dissolving, it is ability to transfer from liquid phase into gaseous phase. This thing we have already know that how if something is dissolved, then how it will be transferred to gas and all these things. That all depend upon the Henry constant. A strippable compound, those compounds which can be easily removed. It name itself suggests a strippable compound, which can be easily removed. Those compounds can be easily removed by water, by air stripping or aeration process. Simple by aeration, you can remove it. Okay, na? Because those are not very attached to the water and all these things. Okay, now or they are not so much in dissolved form. The high volatility and a high Henry constant typically greater than 0 0.1 atmosphere meter square per meter cube per mole. So yes, your answer is correct, that for non-strippable it will be less than 0 0.1, but you should remember the definition. Strippable compounds are benzene, chloroform. Suppose if you have water which contains these kind of gases, then it can be easily removed by simple by aeration process or simple by passing through the air strip tower. Okay, non-stable compound, those compounds do not easily transfer from water to air. They have low volatility and a low Henry law constant. Okay, na. These are typically these have H less than 0 0.1. Remain in water Henry. I hope you have understood it. Uh, Air stripping is effective for volatile pollutant like benzene and ammonia. Non-strip pollutant like other method is like for to remove those material we have to apply other methods such as adsorption, precipitation, or exchange, or any other method also. Maybe advanced oxidation process also. Second question: which of the following factors do not have high efficiency in air stripping process? Then just see before, if you have gone through the lecture, good. If you have not gone through this, apply your simple, like we can just think also that if we want to remove something, then which of the following will won't have such so much effect? This is question number 2. Please answer it. This question will be in your, I think you may have received the weekly assignment, and this type of question will be there. Anyone? Okay, no problem. The correct yes, correct answer is B. Then high pH I will be discussing one by one, okay na. So the first option is high pH. It's favor high efficiency. Air STP is commonly used for removing volatile compounds like ammonia volatile. High favor the conversion of ammonia to ammonium. See, ammonium will be, it has a pK value. I think everyone is aware of pK value, where there is protonation and deprotonation. H plus will be taken by material, the any acid, and it will form some other form. So here, what happened that in case of high pH, this ammonium convert to ammonia, which is more volatile and easily to can be it will easily be removed from the water. So this overall remove the efficiency. So this won't be my answer. Okay. Then we have low temperature does not this does not favor high efficiency. That is, this will be our answer. That is correct answer. The solubility. See, if we want to remove something, then we know that we have to increase its randomness. We can increase the randomness by either increasing surface area, or what we can do that, or we can increase the temperature. Then lowering the temperature will, what will happen that in that case it will still remain in the water only, okay na. So the solubility of water in gases uh, increases at lower temperature, the meaning the contaminant are less likely to volatilize and enter the air phase. This is what I said, that if the temperature is low, then it will remain as it is. It won't be converting into other form, or so higher temperature the promotes volatilization, making the airstrip more effective. So yes, the correct answer is B. But I'm I, I will be discussing other option, that high airflow favor high efficiency. Increasing air to water ratio enhance the mass transfer of volatile compounds from liquid to gas phase. More air means better removal efficiency. Greater packed depth bed favor high efficiency. A greater packed bed provide more contact time between the. This is also like if you are providing more contact area for any, if you are passing the water here and you are more providing, then there are high chances that there will be more contact time between the air and the water. Okay, in this case, again the air stripping efficiency will be increased. This increase the opportunity for volatile compound to transfer into air phase, improving the stripping efficiency. Thus, the low temperature does not favor the efficiency in the air stripping. Okay, so yes, the correct answer was B. This is question number 3. This thing which I have discussed, miss, I have told you few minute ago. What is the most favorable pH for the stripping of the ammonia? If you are listening to me, I have told you the answer of this question. I have told you what is the pK value of ammonia.
Yes.
Anyone any doubt? If some, I think someone was saying something. If someone is saying something, yeah, you are not audible. You can write in chat box. Okay, everyone, please answer this question. D. Okay. Yes, D is the correct answer. Yes. Uh, this is like D is the correct answer. The this is a simple explanation, but um, D is the correct answer. Ammonia strip is process where ammonium ions are converted into ammonia or removed from water. Deficiency of the largely depend on the pH. This thing we have already discussed. At low pH, that is below 7, ammonia exists mostly in NH4, which is highly soluble in water and not volatile, making it strippable. At higher pH, above 9.5, the equilibrium shifted and more ammonium gas is formed, which is volatile and can be stripped efficiently. The most favorable pH for ammonia stripping is typically around pH 10.5 to 11, as this ensures that majority of ammonia is converted into volatile form and it can be effectively removed. So these are not option, and there are chances that someone can say that if we are decreasing the pH, why not to decrease it to uh, why not increase it to 13? Like, but this is unnecessary. If someone is asking, like, if you, yes, we can increase the efficiency, but now imagine that if you are treating something and you are increasing the pH very high, then it won't be like, it will be extra cost and all these things. That's why it is, I have written too high. While ammonia stripping is effective, it is unnecessary to go this high. Strong alkalinity can cause other operational issue, because at this high pH there will be too much OH minus, and OH minus can react with other compounds such as oxygen, sorry, not oxygen, calcium, and it can form calcium hydroxide. Magnesium is there, then it can also react with magnesium, then it will be causing some other problem. See, at this 11 pH also there will be some high amount of OH minus, but it can be controlled. Okay now, but at this pH 13 it will be very high. Any doubt? Okay, next next question. Question 4. Which of these equation is correct for a stripping tower of this is directly from your what do you call, lecture A. Yes, this is like simple. Z is total height of the packed column, height of the transfer unit, and number of the transfer unit. Okay now, HTU measures a measure of how efficient mass transfer occur per unit height. A lower HTU means better efficiency requiring a shorter tower, and NTU is that number transfer represents the total number of theoretical stages needed to achieve the required removal efficiency. So this is there is nothing new. This was just simple formula. There is one numerical question based on this. Z is equal to H2U into NTU. Okay, so the correct answer is this A. Then question number 5. Which of the following is not an advanced oxidation process for treatment of the wastewater? Some of the example which I have shared are that you can, if you recall those things, you can answer from there, or you can just think right now that major the is not an advanced oxidation. Like I have also discussed what is the advanced oxidation, but we are like we want to what do we call? We want to degrade complex organic matter. It is titanium oxide. Two will be in subscript. Okay, na. But I think it's okay. Anyone question answer of this question? Oh, D. You have said acidified potassium dichromate oxidation process. Yes, that is correct answer. That this acidified potassium dichromate is not used. Can someone say where this is used? This is also a oxidizing agent. Acidified potassium dichromate. Can anyone recall where this is used? If you are from civil engineering department and if you are familiar with environmental engineering lab, then you must be familiar with this acidified potassium dichromate. Anyone? Do you recall where this is used? No problem. So I will tell you at the end of the discussion. But if meanwhile, if someone can say where this is used, then you can write in chat box or you can say advanced oxidation process are treatment method that generates highly reactive oxidation to degrade the organic compound. These are typically involve UV, hydrogen peroxide, ozone or catalyst or titanium oxide. These are, but here see in photon what happened that involve H2A2 to generate itna efficient for degrading organic matter. Again, titanium oxide is also a kind of a highly oxidizing in nature, and it is used. Okay. Then we have UV here. Use titanium as a photocatalyst under UV to produce hydroxyl radicals. Okay, now remember in every process we are producing these OH radicals, and these OH radicals is very much like energetic and very much oxidative in nature. It can oxidize anything. Okay, na. Okay. Then we have UVH2 again. This is used to produce hydroxyl radicals. But problem with this does not produce any kind of radicals. Okay, now it is, yes. They see this is a simple what do we call this is simple this compound itself oxidize anything. It does not produce anything. It can directly there is see here the chromium is in chromium 6 form, and what happened that this chromium 6 form react with the organic compound. It is itself get reduced that it conform into chromium 3, and it oxidize the organic matter. Means this compound is directly acting on the organic matter. It is not converting something into OH radicals, then that is reacting with the organic matter. No, this is not happening here. So if you are if you have gone through the environmental engineering lab, then there you must have used this acidified to in COD, that is chemical oxygen demand. Okay, na. So in chemical oxidation demand, we generally use for any organic matter, say in simple wastewater, we determine this oxygen. Sorry, what do we call chemical oxygen demand? And for that what we use this dichromate, potassium dichromate, to see how much oxidation or how much degradation can how much means for that particular organic matter, how much oxygen is required for complete oxidation. Okay, now. So it is a strong oxygen but not considered as AOP. Why not is considered as AOP? Because it does not produce any kind of OH radicals. If you have looked at the definition, only we consider only those as OP which degrade or complex organic matter with the help of radicals. Okay, so the correct answer is D. Someone has already said this. Is it quite good? Till now, only one person is participating. There are eight other people. I request you to everyone, please participate. Question number 6. This is a this is a numerical question. Okay, na. So take your time. This is direct. If you see gone through your video lecture, this is directly from your class notes. What is the electrical energy needed in kilowatt hour per meter cube for the reduction of trace constituents in water treatment plant utilizing the hydrogen peroxide H2O2 UV process where the hydroxyl radicals are generated through UV light exposure. The plant treats a volume of this much meter cube with initial trace concentration at 5 nanogram which decreases to 1 nanogram after treatment. The total electricity input for the process is 1300 kilowatt hour. So you have to just find out what is the need of electrical energy. Every data has been given to you. This much volume of water is coming with concentration of 5 nanogram and is converting into 1 nanogram. Final concentration is 1 nanogram. Take your time. I am giving you 2 minutes. It's 38, so I will wait till 40. Or should I proceed with solution? You can say that also. If you don't want to wait, we can proceed with the solution. 18.6. I hope you have solved it. Good. Yeah, yes, indeed the answer is 18.6. But I hope you have good that you have solved it in very less time. What about others? Yes, the correct answer is this 18.6 kilowatt. This formula is very simple. That if you have to find this electrical energy needed, then what is the electrical energy input divided by total volume into efficient this we have to take the log of ci into cf. This is a direct formula. Okay, now everything has been given to you. And miss, I don't see, but I think uh, there is a proof for this thing also. If anyone have any kind of doubt, I'm just looking into the proof. Is there any proof? Because I have also directly put the formula and found out the answer. I'm not gone through. So right now I cannot recall from where did this formula come. Okay, na. But for electrical energy, we have to use this formula, that is electrical energy input divided by volume into log of initial concentration divided by final concentration. Okay, then other question, which is the catalyst in what is the catalyst in the advanced oxidation process? Catalyst means that element, yeah, that compound which increase the rate of reaction. Okay, na. So out of in oxidation, we know that in advanced oxidation process we have to produce OH radicals. So which of these are catalyst? Okay, na. There is a first option, that is it UV slash H2O2, or H2O2 titanium oxide and iron, or all of these. One, I have got one answer. Is the correct answer is D, that is in advanced oxidation process, catalyst play a crucial role in generating highly reactive or which break down the organic matter. Catalyst, UV light and ozone are ozone are catalyst here. What does UV break down the oxidation peroxide into hydrogen radicals, and ozone and UV further enhance the radical generation. So there is first breakdown of H2 into OH radicals, and what happens to enhance the process, this UV and ozone increase the efficiency, overall efficiency. Then second option is H2O2 titanium oxide. Catalyst is titanium oxide and iron. H2 again, titanium acts as a catalyst under UV, enhancing the production of radicals. Okay, na. And here in iron catalyze the decomposition of H2O2 into hydrogen radicals. So you should know the function of each of the every compound or chemical which is being to produce OH radicals. Then we have third option, that Fe2 plus, here catalyst is iron 2 plus and electrochemical reaction. If Fe2 plus H2O2 and UV combined, we know that it is known as photophenton process. UV light enhance the photon's reaction, boosting the hydroxyl radical production. Again, in this process, iron is Fe2 plus is used. Okay, now it uses electrical current to regenerate Fe2 plus, maintaining the radical production. So what happens in electrophantom? We use the electricity to generate Fe2 plus, and this Fe2 plus makes sure that more and more OH radicals are produced. Okay, now ozone again here in the system, ozone react with H2O2 to form, and these all go in cycle to produce more and more OH radicals. So since all these methods involve catalyst in EOP, the correct answer is A, D. Organic matter removed by oxidation through reaction with. This is very simple question. Directly, very easy. These questions are just for your practice, so that you can be more familiar with the basic things. B option. I think there are other people are also in this group. Why they are not bothering to answer? Okay, no problem. Just it will be good if everyone participate. Else, no problem. This is a very simple question. The correct answer is D. In wastewater, organic matter are removed by oxidation, where strong oxidizing agents break down the pollutant into simpler or less harmful compounds. The most effective oxidizing for the process is the hydroxyl radical. This thing we have already know, very reactive, non-selective, meaning they can rapidly oxidize a wide range of organic pollutants, more powerful than oxygen and hydrogen peroxide in breaking down the complex organic, used in UV Fenton process and ozone waste OP to degrade contaminant. Hydrogen is not oxidant; it is a reducing agent. Water itself does not oxidize organic matter. O2 is oxidizer, but not a but much slower and less reactive than hydroxide. Correct answer is UOH radical is correct answer. Question number: which gas is produced by subjecting oxygen to high electric voltage? I'm just coming in 1 minute. I request everyone to please answer it. D. I have we have received two answer, that is ozone. Yes, this is correct answer. That when O2 is subjected to high electric voltage, such as in process called electrical discharge or corona discharge, ozone is produced. This occurs because the high voltage splits O2 molecule into individual oxygen O, which then reacts with O2 molecule to form O3. Okay, now this is, see, this reaction is also happening in the atmosphere. Also, you might have heard that in the presence of UV rays, there is a ozone formation. So that is happening. Why? Like due to this region only. This was out of context, but if you want to recall that how the ozone is forming at the in the atmosphere, then there is something similar region, and uh, then there is a breakdown of ozone also due to CFC. This ozone is getting broken, then all things are very linked up. So here also, in presence of sunlight and UV, ozone formation is occurring at in the atmosphere. But if on the ground, in our wastewater treatment, we are subjecting our oxygen at very high voltage, which convert into two oxygen atoms, and one oxygen atom react with the available oxygen to form O3, that is ozone. This is other option are carbon dioxide is produced by subject to burning process. If you burn any carbon containing material in presence of oxygen, then there will be production of CO2. Carbon monoxide, if we are burning but in absence of, like we are restricting the pressure and temperature, then there are high chances that CO will be produced by incomplete combustion. There is a full combustion, that is we are providing sufficient amount of oxygen, sufficient amount of pressure. But if there is a incomplete combustion, when we are not providing sufficient oxygen and sufficient uh, pressure, then this CO will be produced. Pure O2 not produced by high voltage, it will be dissolved into, this is another thing. We know how CO2 is produced by this photosynthesis and all these things. Then correct answer is D, that is ozone. Question number 10. Read the question carefully. Which of the following is correct regarding sulfate radicals and hydroxyl radical OH minus? Oh, there is this thing. 1 minute. We have got one answer. D. 1, 2, 3. All three are correct. The first option is sulfate exhibit higher energy barrier and selectivity than hydroxyl. Sulfate radical is more selective and tends to attach the organic matter primarily to the electron transfer pathway, where OH is non-selective and involve electrophilic addition to the pi bond of unsaturated hydrocarbons and aromatic H abstraction in the aliphatic carbons, electron transfer in the halogenetic carbon. And third option is uh, this hydroxyl and sulfate radicals have a smaller redox potential, but the chemistry is dissimilar. We have got one answer. We have got two answer. Good. So we will be seeing one by one. The correct answer is D. Yes, all three options were correct. Sorry. All three options are correct. The sulfate exhibit higher energy barrier and selectivity than had peroxide hydroxyl radical. Correct. The sulfate have higher energy barrier and more selectivity than it tends to more specific attacking certain types of organic compound, often showing more selectivity reactive than this is like due to its nature and all this thing. So I won't be going into its chemistry why this is happening. For that you can go to the video lecture. But the option one was correct. Then option two is the sulfate radical is more selective and tend to attack carbon primarily through this thing is also correct. Okay, now again for this miss I am writing in very brief, but if you want to discuss, if you want to go to the more detail, you are always welcome to go and look at the lectures. Correct is more typically attack organic carbon through electron transfer mechanism. So there will be electron transfer from this molecule to the organic matter which is attaching involving oxidizing the targeting. On the other side, OH is less selective and reacts to the variety of pathway including electrophilic addition. Means here there will be some kind of substitution, then there will be transfer of electron and all these things. Here also there will be transfer, but in this method only transfer mechanism involved, but in OH radical more complex mechanism are involved. Okay, now we can see here some of the mechanism, that addition to the pi bonds, hydrogen abstraction from aliphatic compounds, and electron transfer in halogenetic hydrocarbons. So these are several ways by which OH radical attacks. Correct, both have similar potential, meaning they both are powerful oxidant, but their chemical behavior differs significantly. O is highly reactive in broad range of reaction, while it tends to more selective in the reaction. So the correct answer is D. 1, 2, 3. Then we have another question. Take your time. Take your time. Solve ABC. Okay, na. Again, this is question from, what do I call, your PDF, that is lecture notes.
हेलो
Yes.
सर गुड इवनिंग सर.
Good evening. Good evening.
सर एक मेरे को असाइनमेंट वन रिगार्डिंग क्वेरी थी, तो कैन आई आस्क?
Yeah. Assignment 1. Yeah, you can ask.
एक्चुअली सर उसमें हमने जो क्वेश्चन आंसर का मेरा ब्लॉग बना उस पर क्वेरी पोस्ट करी थी, क्वेश्चन नंबर 8 और क्वेश्चन नंबर 10 रिगार्डिंग. वी रिप्लाइड टू योर आंसर करेक्ट, बट मार्क्स इज नॉट अपडेटेड ऑन स्वयं पोर्टल.
Just 1 minute. Let me check. One, just give me 1 minute.
यस, एक्चुअली हमने सर डेसिमल के अप टू 3 डिजिट तक आंसर पुटअप किया था, लेकिन यू हैव कंसिडर ओनली अप टू 2 प्लेसेस.
Mm, just give me 1 minute.
श्योर 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 सर.
In question number 8 means regarding this question, peak and minimum flow of reaching ETP.
यस यस सर.
What was your answer? What you have? What was your answer?
एक्चुअली सर 28 पॉइंट समथिंग 2 डेसिमल, अभी एग्जैक्टली तो याद नहीं है, मेरे को देखना पड़ेगा.
हाँ हाँ.
तो हमने सर बहुत सारे कैंडिडेट की क्वेरी थी और सबने पोस्ट भी किया है ब्लॉग में.
ठीक है. मैं अच्छा क्वेश्चन नंबर 8 एंड क्वेश्चन नंबर 9 में.
क्वेश्चन नंबर 8 एंड क्वेश्चन नंबर 10.
क्वेश्चन नंबर 8 मैं नोट डाउन कर लेता हूँ. मैं एक मेल फॉरवर्ड कर दूंगा और मैं अपना पूरा कोशिश करूंगा तुम सबको नंबर मिल जाए.
यस यस, थैंक यू सर. एक्चुअली वो अफेक्ट करेगा मार्क्स पे हमारे,
हाँ
इसलिए.
ठीक है. मैं मेल वो मैं करेक्ट करवा दूंगा.
हाँ सर, वो क्योंकि बहुत सारे कैंडिडेट्स का सर अभी आप मैसेज भी देख सकते हो.
हाँ हाँ मैं देख रहा हूँ. ठीक है. मैं इसे करेक्ट करवा दूंगा.
श्योर श्योर सर, थैंक यू सर.
ठीक है. अगर नहीं हो तो एक मतलब मैं अपना ईमेल आईडी लिख देता हूँ. आप मतलब मुझे आप एक बार कर सकते हैं मेल की अभी तक नहीं हुआ है. ठीक ना.
श्योर श्योर सर.
लेकिन इसमें थोड़ा सा टाइम लगेगा, मे बी 4-5 दिन. तो आप 4-5 दिन का वेट कीजिएगा.
नो 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 प्रॉब्लम, नो प्रॉब्लम सर.
ये मेरा हम्म, ये मेरा ईमेल आईडी है. मैं अपने चैट बॉक्स में लिख दिया हूँ mprakash23@. आप 4-5 दिन बाद अगर नहीं हुआ देन आप मुझे एक बार कांटेक्ट कर सकते हैं.
श्योर 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 सर.
ठीक है. ठीक है.
थैंक यू सर, थैंक यू वेरी मच सर.
ठीक. ओके. किसी को और कोई डाउट मतलब पुराने किसी लेक्चर या असाइनमेंट से? एक्सेप्ट द आंसर बोथ इन हम. हाँ. मिस आई विल मेल. आई विल try my best that you all get your deserving marks. So I think miss like you this are you seeing my slide? This was I think if you are see there is a always range like sometime what मेरे हिसाब से क्या हुआ होगा कि जो आंसर चेक करने वाले ने वो रेंज हटा दिया होगा, जिसके कारण वो लेकिन वो रेंज जब कभी भी बढ़ा सकते हैं तो वो आ जाएगा सही सही आंसर. सिमिलरली इस क्वेश्चन में भी पीएच 4.73 अगर हो सकता है किसी ने 4.731 बड़ा ऐसे कुछ लिख दिया होगा तो मे बी वो डिडक्ट कर दिए होंगे, बट ये सही, अगर 4.73 या 4.72 भी किसी ने लिखा हो, या 4.7 भी किसी ने लिखा हो, तो उसको सही माना जाएगा। अ, ठीक है, मैं इसके अलावा किसी को और कोई डाउट? ओके, देन हम आगे लेट्स मूव फॉरवर्ड विथ दिस क्वेश्चन। ये क्वेश्चन, आई आस्क एवरीवन, आई रिक्वेस्ट एवरीवन, प्लीज सॉल्व दिस क्वेश्चन। So the question is very simple, and it's directly from your lecture notes. Air stripping tower is designed to remove ammonia, that is NH3, from the wastewater. The initial ammonia concentration is 50 milligram per liter, and it needs to be reduced to 5 milligram per liter. The wastewater flow rate is 500 meter cube per day, and the Henry constant for ammonia is 25 degrees Celsius. Sorry, at 25 degrees Celsius is 0.75 atm. Okay, na. See, there is like this. You have to. I have to check the unit whether it is correct or not. Just let me. Just. I think it depend upon how we are writing. Uh, uh, Henry constant is this thing. Oh, it's correct then. Actually, see how sometime Henry constant, like if it is written 0.75 atm, then what will happen that your if you look into the formula, like how generally this Henry constant formula is written, it is written in the form of this form, that is pressure divided by concentration. Okay, na. So, like, how to explain this thing? Generally, the for if you I will show you the Henry constant chart. So see, this is the correct means, like most of the time at several places na. So at several places you will be seeing that this Henry constant is written in the form of atm per mole per liter. Most of the places you will be seeing this thing only. Okay, na. atm per mole per liter, that is atm per uh, molarity. Then formula is also Henry constant is equal to pressure divided by concentration. That's why we say that this concentration will be go on right side. Then we say that concentration is directly proportional to partial pressure, and depending upon the Henry constant, it will either dissolve or redissolve. Okay, na. So the atm, but sometime, like in this problem, they have just only written as atm. Then if we are writing atm, then in my formula we have to write our this concentration the in a unitless quantity. Then there we are using this concept that see here when when we are writing Henry constant, then 0.75 atm mole of ammonia divided by mole of air. Like we are multiplying this atm into mole of like we are multiplying this Henry constant of 0.75 atm into the molar fraction of ammonia in air, okay na, divided by molar, this concentration is in water only. Then there is additional multiplication by this term, okay na, because if you look at this table and if we look at the ammonia, I think there ammonia, it is Henry constant is 0.037, okay na, at 25 degrees celsius it is 0.037, because they have, it is not being, it is with it is with it is written after dividing it by the mole fraction in the air, okay na. I hope miss what I'm trying to say. So don't get confused when it is, when the Henry constant unit is written is in atm, or whether it is written in the atm per molarity. Most of the time you will be seeing in the atm per molarity only if you are appearing for say gate examination or something. Every data has been given to you. First you have to calculate the mole fraction, mole fraction, um, the mole fraction of the ammonia in the gas phase at equilibrium using Henry law, and the minimum amount of air required for complete ammonia removal. Okay, now these are the given data that C naught is 50 milligram per liter, C is 5 milligram per liter, then Henry constant is 0.75, then gas to liquid ratio is 1500 meter cube air divided by meter cube water. Total pressure is 1 atm. Wastewater flow rate is 500 meter cube. I have changed the data only in this question. The first question is to find the mole fraction initially and final. Okay, now before treatment and after treatment. The mole fraction will be given by moles of ammonia divided by moles of ammonia plus moles of water. Then moles of initial mole, then then I think one slide has been missed here. So, given the concentration of, you know, the concentration that is this thing 50. Can anyone say, how can anyone tell? Miss, you can find the mole of ammonia now. You know the concentration that is this thing 50 milligram per liter. Then 50 divided by molecular weight of ammonia. Molecular weight of ammonia is 14 plus 3, that is 17. Okay, as it is in milligram per liter, then you have to multiply it by 10 ki power minus 3 to convert into gram. Then if you multiply it, you will be getting the mole of ammonia, okay na. Can anyone say how to find the mole of water? पानी का मोल कैसे निकालते हैं? एनीवन? सी पानी का मोल 55.56 होता है, लेकिन एनीवन कैन से हाउ टू फाइंड दिस मोल? This is simple. Suppose if I have 1 liter of water, say 1 liter of water, then we know that what is the density of the water? What is the density of water? Anyone?
1000 gram.
Huh. That is correct. Yeah, 1 gram per liter. It is correct? No, one. Sorry, just one minute. Let me check my calculator. I don't know. Huh. It is 1000. It's not liter. It is centimeter. 1 centimeter per cube. Okay, na, centimeter per cube. Then it is 1 gram. If you convert centimeter cube into liter, then it will be 10 ki power 3 liter. 10 ki power minus 3 liter. Okay. Then or you can say the density is 1000 gram per liter. So you know that in 1 liter you have 1000 gram of water, and what is the molecular weight of H2O? That is 18. 16 plus 2, that is 18. So if you divide 1000 divided by 18, 1000 divided by 18, the answer is 55.56. So remember that when you take 1 liter of water, it has a mole of 55.56. 55.5555, we wrote at 55.56. So you know the moles of ammonia, that is 50 divided by 17 to 10 to the power minus 3. Moles of water, that is 1000 divided by 18. You will put it here and you will be getting the mole fraction, that is for initial, that is when the naught is equal to C naught is equal to 50. Here 50 milligram per liter, 50 milligram per liter. Now the second part of the question was to find the mole fraction at the outlet, that is after the treatment. Here the concentration is 5 milligram per liter. Then again it will be 5. You can see that one as 10 has been removed, so here it will be point 0, or you can just simply rewrite 5 divided by 17 into 10 ki power minus 3. 10 ki power minus 3. Then it will be 0.293, 20, then mole fraction is 5.3 into 10 to the power minus 6. Now the B part is simple. What was the B part? B part, the mole fraction of ammonia in the gas phase at equilibrium using Henry constant, Henry gas law. Then here we will be applying the concept of Henry law. Okay, then we know that using the Henry law, this mole fraction is equal to Henry constant into divided by pressure, or hmm, then everything has been given to you. Pressure has been given to you in the question. Pressure is given that 1 atm is there. Okay, so we'll be substituting all the value. Okay, na. uh, uh, for initial condition mole fraction is 5.3 into 10 to the power minus 5, and for the final condition it is 5.3 into 10 to the power minus 6. uh, okay, I hope this is clear to you. You will be like, so Henry constant is 0.75 already given to you. Remember, normal formula when we write in the form of, don't get confused. Here we are writing in the form of mole fraction. That's why we are. If someone asks that what is Henry constant, you will just simply say that Henry constant is H is equal to pressure divided by molarity, that or concentration. But here you as your Henry constant was in the given question, as the Henry constant was in the form of atm. So that's why we are making some modification. And what kind of modification we are making, that I have already said you. Say, I'm repeating same thing again and again so that you can understand. Here you can see that we are writing in the form of mole fraction, as the unit is in without any concentration. That's why we are, and we know that for mole fraction there is no need of, mole fraction doesn't have any unit, everyone, because it is the ratio of moles, so it does not have any unit. So that's why here also I have written in the form of mole fraction of ammonia in water into mole fraction of ammonia into gas. This thing we have to find mole fraction in the gas form. So initially everything you have already, you have find in the water, xg the mole fraction in water, okay na, we have already found it, okay. So then we will just divide it, we will put the value and we will be finding the ammonia concentration in air initially and ammonia concentration in air after the treatment. Okay, then finally this is also simple question that you have to find gas by liquid ratio, sorry, the question was to find the this thing, minimum amount of air required to complete ammonia removal. Okay, now for that also we have direct formula. This thing has been also directly taken from you, okay now, sorry, directly taken from the lecture, this lecture notes. To determine the gas liquid ratio, use the following equation, and detail of this equation has been already shared with you, how this ratio is, how miss how this equation is has come up, and all this thing here, everything has been given to you. Everything is given to you, pressure is given to you, Henry constant is given to you, initial concentration minus final concentration from here. Since the GL is 15 which is greater than 12, uh, which is complete is easily available in this design, okay now. uh, so it was asked to you that already GL by this thing is 1500, then the minimum amount of air required, so minimum amount of required is 12 meter cube per meter cube of air, but as you are providing 1500 meter cube, then that is more than required required amount, okay na. Any doubt in this thing? Here just you have to find out the what is the gas by liquid ratio, there was no need of this data, okay na. Any doubt in this question? Here you can see that here they have just find out the 1.3 mole air, they have found it in the form of mole, but overall that overall the formula which is used is this thing only, okay na. Coming to the next question again, it is very simple question, but I have assumed one thing that you know the kinetics, like how this thing must, you must have read in your class 12th, that how first order reaction is there, second order reaction is there, zero order reaction is there. So based on this thing, only there is one little bit trick here, not trick, there is a concept of another order. There is a question that the wastewater treatment plant uses to process the degraded Benjamin in the water. The initial Benjamin concentration is 100 mg per liter. The target reduction is 90 percent within 30 minutes. The hydroxyl radial concentration is this thing. Oxidation rate is this thing, and there is one concentration is maintained at 1.1 into 10 to the power minus 9 meter. Then you have to calculate the time required to for this conversion, that from 9 in uh, uh, time required reaction using the first, like if it is like you have to do within 30 minutes, but you have to find out, man, how much time will be required for for concentration to be getting reduced by 90%. Means from 100 milligram per liter, मतलब microgram per liter, to 1 microgram per liter. I hope everyone is aware of this first order, second order. This question is simple until or unless you know the concept of this first order, second order, zero order. Okay, so here it is. See, here it is written. Every given data is here. Uh, Initial benzene concentration is this. Final benzene concentration is we have converted into mole. Can anyone say what is the molecular weight of benzene? Benzene is like this. Then it is C6H6. The molecular weight is 78. Okay. Then if you convert given 100 milligram per liter, if you multiply 100, if you divide 100 divided by 60, 78. It is 1.2 into 10 power. Add it in microgram, that is 10 ki power minus 6. Okay, na. So that's why it is in. Similarly, if it is 90% removal, then it will be 10 microgram per liter. That is 1.28 into 10 to the power minus 7 mole per liter. Then K constant is given to you 5 into 10 to the power 9. And there, it is always said throughout the reaction, this hydroxyl concentration is constant. Okay, na. So now this thing, we know that if it is now, remember, as this is given to you in a if you go through the kinetics, see, I'm little bit detouring from the actual discussion. I hope you are, but whenever you are solving this radical question, that is which radical, this concept question comes, that this theory comes, like suppose we have a reaction of A plus B is giving, say suppose C plus D plus E. E is kind of a some another term. Okay, now. So if you write the K terms, K of the reaction, it will be C. Miss, if you write the rate reaction, like how miss what do we call, how to explain this thing? I will just show you some my previous slide, like if I keep writing, then it will take a longer time. Arey yaar, I don't recall where it was. I will just show you simply the books. That will be the best. See, here it is. You might be finding it. uh, we are suppose there is one reaction going from a a a and b reacting giving c and d, okay now. Then the reaction rate constant will be written as dc by dt into k into some constant, okay now imagine that in this function there is one term which is always constant. Then what will happen, that that constant will be multiplied by with this already reaction constant. Suppose if this reaction is converting from a to b, a and b reacting converting into c and d, then there is some reaction constant already. But the situation is that there is some particle or some molecule whose concentration is constant throughout the time. Then what will happen, that that reaction will won't called as a first order reaction. That reaction will be called as a pseudo first order reaction, because the overall reaction is behaving like a first order reaction, but due to presence of one molecule whose concentration is constant throughout the time, is not decreasing or increasing, then it that reaction, that concentration itself become a constant for that kinetics. So what happened, that we multiplied that concentration with the given reaction constant, and the overall reaction is known as pseudo first order kinetics. So there also, so currently what will happen, that uh, I will be writing simply as k which is given there, but I will multiply this k with the concentration which is given in the question or given in the system, because that concentration is not changing, and we will do the all the calculation and all this thing. So here, so this question I am discussing because you will, if you are in somewhere, you will be getting this question like this. Degradation is first order and there is a concentration of OH radical, and sometimes you will get confused that what to do with the OH radical concentration. Then you have to multiply apply the concept of pseudo first order kinetics. We know that Benjamin concentration, it will be decreasing at as first order. Then we will, if you do the all the integration, then you will be finding this reaction, finding this equation. Then from here you will be finding the time required. Time will be, if you take ln on the both side, time will be ln t be concentration divided by k observed. Now see, this thing which I have already know. Now the k is given to you as 5 into 10 to the power 9 mole per second, and OH radical concentration is always fixed at 1 into 10 to the power minus 9. So the no, new k observance will be 5 into 10 to the power minus 9 into 1 into 10 to the power minus 9, that is 5 second. Means like your rate constant will won't be 5 into 10 to the power minus 9, but it will be k observance will be 5 into 5 into 5 per second. You will be putting this k here, you will be putting k here, initial concentration, final concentration you all know. Then you can find the time required. In question it was saying that we have to do within 30 seconds, but here you can see that the target was achieved within few seconds, that is 0.46 second only. I hope, I don't know, anyone any doubt in this question? Anyone have any doubt? If you want to read more about this order kinetics and all this thing, then I suggest you this book name is this thing, surface water quality modeling by Steven C Chapra. It is available online, just search on internet, surface water quality modeling Steven C Chapra. Okay na, you will get this thing, this book. And if you want to read about other thing, which I was saying, that Henry Constant and all, Henry Constant, more about Henry Constant, then I will suggest another book, and that book name is This book, Water Chemistry by Mark M. Benjamin. This question is very really good book in context of environmental engineering, and if you are working with the water chemistry, okay, na here you will see in this chapter Henry Constant. You will, I think, it will be in basic equity chemistry reaction, potential energy, then acid base, use of log CPA, software titration, gas liquid equilibrium. This chapter number 9. Chapter number 9 to know about this thing, Henry Constant, how this is used and all this thing. Okay, na. This is really good book. Go and read. Miss, this book. This will be book is also available online. Okay, na. This is really good book. Here you will see more detail about Henry Constant and all this thing. How you will see real experiment. How this Henry Constant is used to determine many things. Okay, na. And in this chapter, chapter number 2 is about reaction kinetics. Chapter number 2, reaction kinetics, fundamental of reaction. Go and read this book. My suggestion. Moving forward, try to answer this question. See, I am like, if you have any kind of doubt, you can ask. There are high chances that I might not be able to explain in a better way. So, if you means like sometime I am in flow, I think I am explaining in a better way. But you are the audience. I miss how you are taking the things. I don't know. So you can always ask me to stop. फिर से explain करो. And I have tendency to repeat things like I during discussion. I always tend to speak one thing twice or thrice. So I don't think you should have any kind of problem. So let's don't go there. Just I'm saying that if you have any kind of doubt, you can ask. A. In UV waste oxidation degradation efficiency of organic polyethylene depend upon the multiple. Which of the following will most significantly influence the effectiveness of generation in the process? The correct answer is B, not A. Oxidation potential. While hydroxyl are powerful oxidant, though their oxidation alone does not determine how efficient they are generated in. Means like, see, we are talking about its production. Okay, na. So how miss like how efficient OH radical will be produced. So it does not depend upon the uh, oxidation potential. Okay, now correct answer is B. Correct hydroxyl radicals in UV slash H2O2 systems are generated by photolysis of H2O2. If H2O2 concentration is too low, fewer radicals are produced. If it is too high, excess H2O may act as radical scavenger, reducing the efficiency. Thus, an optimal H2O concentration is critical for maximizing the radical production. I hope this is clear to you. Other option, organic chemical structure of the pollutant affect the degradation, but core process of the independent of the pollutant type. Redox potential of the wastewater. Although redox ORP reflects the oxidative nature, it does not directly dictate hydroxyl radical formation in H2O2 system. Another question. In air stripping, what is the primary reason for increasing the pH when removing? This is the third question related to ammonia. I guess that everyone should answer it. What is the primary reason of increasing the pH? Anyone? Question are very simple. If you are listening to the what do I call lectures, you will be able to answer C. Yes, C the correct answer. To convert ammonium at gaseous at high pH that is equal to 10, ammonium will shift to the volatile ammonium gas, which can be then easily stripped from the water. Yes, C is the correct answer. Question number 15. Which of the following condition would improve the efficiency of an air stripping tower? Which of the will improve the efficiency of an air stripping tower? Anyone, please, any answer? Okay, no answer. The correct answer is B. Using Henry constant law, using a Henry law constant compound. A higher Henry law constant means the compound is more volatile, making air strippable more effective. I hope these are clear to you. These are questions from your lecture notes. I am not taken any from any. These are directly from. If you have gone through the lecture, you will be able to answer this question. Water flow cannot increase the efficiency. Okay, na increasing air to obviously decrease. If you decrease the air to water ratio, then that will also not work. Packing material with surface area no smaller. We have to use a packing material of higher surface area. Okay, but if you use a Henry law constant compound like then obviously it can be easily stripped away and then we can increase the efficiency. Oh, question number 16 has been, I don't know where is question number 16, but question related to Fenton's oxidation process. Why is Fe2 is preferred over Fe3 plus? Fe2 plus is preferred over Fe3 plus. Fe2 plus is more stable in acidic environment. Fe2 reacts with H2O2 to generate hydroxyl radical while Fe3 does not. Fe3 increases the solubility of H2O2. Fe2 directly oxidizes pollutant without needing H2O2. What? We are not. I have said. Sorry, miss. You are not able to see my presentation. What about now? Are you able to
Now
see?
okay. Now okay. Yeah, I'm seeing.
So where you were able to see these questions? Yes or no?
Yes, the previous one. Yes, I am the same. The previous one.
This question?
Now it is also.
Yes, sir, we can see now.
Okay, then I
No,
have
now
a
I am not seeing. I am not seeing.
okay. Then there might be some technical issue. Sorry for that.
Please correct it. Okay, yeah.
Okay, just try to answer this question.
Okay. Sorry, I am not seeing the question. Sorry.
Sorry,
Yes, I am not seeing. It's not okay.
you are not audible. There is some problem in your voice. Miss audio. You can write in chat box. Yeah, you can. I'm not able to hear you. Okay, I will go through this lecture. The correct answer will be B, which is directly which we have already discussed that. See, uh, uh, for production of here we are like hmm. So we have to produce OH radicals. Okay, now. So here, what will happen that in what will happen that this Fe2 Fe3 plus itself does not exist so much. Okay, na. Hmm. So why Fe2 plus is preferred? Because it can easily react with H2O2. Okay, now, but Fe3 plus does not react with H2O2 because you see, if you look at the reaction, I will show you the reaction. Where it is? Where is the reaction? Titanium oxide, iron. Here you can see. Here you can see that uh, for for this reaction, it needs to uh, mm, like it's not written in electron form. But in a simple way we can say that for this reaction to happen, there should be something which has to lose one electron. Okay, now, then what will happen that Fe2 plus will lose one electron and it will form Fe3 plus. But Fe3 plus cannot lose any more electron. That's why it cannot react with H2O2. Okay, now, that's why H2O2 is so what will happen that Fe2 plus will react with this H2O2 and it will convert into this what do we call Fe3 plus, and again this Fe3 plus will react, but it won't form any H2OH radicals. Okay, na. It means this go on cycle. In any reaction you will be seeing that at no places where Fe23 is reacting to form OH radical, always it will Fe2 plus is forming to is reacting and forming this OH radical. Okay, so I hope this is clear to you. Means this was not so. I hope. So the correct answer was B. Uh, c- then 18th question, which I hope you are able to see my screen this time. Uh, this question was already there. Question number, which of the following is the most? I have already sent you the answer. Which of the following AP is the most suitable for degrading persistent organic pollutant that do not absorb OB? Obviously, if the uh, 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 this the ozone slash H2O2 system generates hydroxyl radical without requiring the pollutant to absorb UV, making it effective for non-UV absorbing compounds. So this was a direct, again direct question from your lecture notes. Oh, again, I don't know. Hmm. What is the primary advantage of sulfate radical based AOPs over hydroxylide radical? See, we have already seen the question that related to sulfate versus hydroxyl. Sulfate is electron transfer, but OH is complex method. But again, there is one question, and the answer is this. Correct answer is A, that sulfate radicals have longer lifetime and are more selective. See, H2O2 itself is a very reactive material. If you, it will just simply oxidize and things, and its other part, that is OH radical, is more reactive. So it is not a stable, it will just somehow react with its surrounding and it will convert into some other form. But on other hand, sulfate radicals are very stable, and it is like it will works for longer time. Okay, na, the radicals have a longer lifetime, are uh, more selective in the oxidation, have longer lifetime than hydroxyl, and more selective, making the effective in certain application where hydroxyls are too reactive. Hydroxyl radicals are really too reactive. Okay, then last question of the day. Everyone please try. In electrophanton process, what is the main advantage of generating Fe2 plus electrochemically? Anyone? D. It reduces the reaction time of the pollutant degradation. The correct answer is B. It prevents the formation of sludge by controlling iron concentration. I'm not going to explain this option, but D, reaction time is already very low in any oxidation process, this AOP. Okay, na. So use of electricity does not cause any kind of this. The main advantage is this thing that electrochemical continuously regenerates Fe3 plus Fe2 plus from Fe3 plus, reducing the sludge formation and improving the process removal efficiency. You can see from here also. This is here in this electro where, just let me go through electro. Here you can see that there is a continuous conversion of Fe3 plus. See, first what will happen, that if you go through the uh, simple reaction, and if you combine it, if you can see that here there is a formation of Fe3 plus, that is forming some another kind of sludge. Okay, na. But here what is happening, that Fe3 plus which was forming also is getting converted into Fe2 plus, which will more oxidize, which will be again reacting with H2O2 to performing to convert more OH radicals. Just go through this, combine those two process here, then you will be able to understand it. Okay, na. Means if there is no sludge problem is here, but in this process you will see some kind of sludge is also forming. Okay na. uh, j- uh, sludge needs to be separately disposed of. Thus consequently Fe2 plus form iron sludge at a typical water, because Fe2 plus react with OH and all this thing and combine it form PPT OH, FeOH whole thrice, FeOH whole thrice, yeah. But in this case no sludge problem, you will be seeing no sludge problem. So that was for that's all for today. I don't think no more question. But if you have any kind of doubt, you can ask right now, or we can end the session. We have 4 to 5 minutes. No doubt, not from for this session only. If you have any doubt from big two or big one, you can ask. And one, I think we won't be meet. I will be Miss NPTL team will be sending you one notification. Maybe the next session will be happening on this Friday only. Okay, now because next week I have to go to one marriage and all these things, so I want to be available on next Tuesday. So I will try to schedule this week four discussion on Friday or Saturday. Okay, now I will let you know the time. But yeah, so I will request you to please keep in this in my thing in mind and join on Friday. Most probably it will be on Friday. Miss, I have to see my schedule, but most probably it will be on Friday only. Any more doubt? Anyone? So okay, I think there is no doubt. Then I am ending the session. Let's meet on this Friday. Tata. Good night, everyone. Call cannot end for try again.